Okay, so for this video, let's talk about the shell method and the washer method. Okay, so shell versus washer. Okay, so those two methods are common methods to solve the volume of a solid by revolution, and we can look at one problem here. So suppose we have a let's see, maybe we have a region, let's see, bounded by y equals square root of x, and then x equals 4, and also the x-axis. Okay, so this is the region. Okay, and then I would like to revolve this region about the y-axis and then to form a solid. Okay, so basically it's going to be something like this. Okay, but it's a solid, so it's going to be a 3-dimension here. Okay, and maybe let's first use the shell method to handle this. So the shell method, first of all, you can see that we can draw a shell here. So so basically, okay, so this is what we can do. And well, to make things more straightforward, we can trying to draw this more accurately. Okay, so this actually is going to be a shell. Okay, and as you can see that the volume of this shell is the volume of the shell is equal to the circumference here, which is 2 pi times the radius of the circular surface. So, and then time the height, and also time the thickness. Okay, time the thickness. So what we do here is anytime when we're trying to construct this shell, the thickness of that shell is always d of x. Okay, so you can see it's a small increment for the shell here, and so the height, which is here, and then the radius, okay, which is this part is the radius here. So the volume of this single shell, which is 2 pi times r times the height. Okay, so why this is true, the idea is, if you cut this shell and then it turns out that if you cut this shell, let's see, from here and then you flat it, it's gonna be a rectangular. It's gonna be a rectangular format. Okay, so the length for this part, which is exactly the circumference, this is the height, and then this is the thickness. Okay, so in this problem here, as you can see that my x, which is exactly the length, my radius r, which is exactly the length for this part, and we can denote this as x here. So my radius is going to be x, because my x is moving from 0 to 4, right? So when the radius is very small, you're going to have a very tiny shell, and then as long as your x is moving, is becoming larger, the radius of the shell is becoming larger, and also the height is becoming larger. Okay, so you can imagine that this is in 3D. And then the height, obviously, when x is here, the height, which is the corresponding y value, which is denoted as square root of x. So the height, which is square root of x. Okay. So right now, put all these pieces together. So the volume of the shell is 2 pi times x times square root of x times dx. Okay. So right now, we formulated the volume of the shell, and then the volume of that solid, which is integration from 0 to 4, right? And then the volume of that shell, which is 2 pi x times square root of x dx. Okay. And it turns out that this integral is very easy to evaluate it. So we can factor this 2 pi out, 0 to 4. X times x to the power half, right? So, which is x3 half dx. So we write it into the power, so it's easy for us to find the antiderivative. That is 3 half plus 1 over 3 half plus 1 from 0 to 4. Okay. And, we can do some simplification. So this is 5 over 2. So it's going to be 2 x to the power of 5 over 2 over 5 divided from 0 to 4. Turns out this is 2 pi times, just to plug 4 in, right? So this is 2 times 4 to the power of 5 over 2 over 5. And then minus 0. Okay. Turns out this 4 to the power 5 over 2, we can do some simplification because 4 equals 2 squared. So 2 squared raised to the power 5 over 2, then over 5. And then this is going to be 2 to the power of 5. Okay. So 2 pi times 2 to the power 5 times 2, which is 2 times 2, 5 over 2. So it turns out this is going to be 2 to the power of 5 is 32. This is 64. This is 128. So it turns out this is 128 pi over 5. Okay. So that's how do we use a shell method to solve this volume of this solid. Okay. Now I want to show you how to use the washer method to solve this problem. Exactly the same problem here. Okay. And I still want to draw this graph. So this is here. Okay. This is here. Okay. So this is still y equals square root of x. This is 4. This is okay. This is xy plane here. Okay. So the difference between this shell method and the washer method is the washer method actually it borrows the idea of the cross section. Okay. Take a look at this again, guys. This think about it into dimension 3 here. So this if I make a cross section that is perpendicular to the y-axis here, and then turns out you're going to have something like this. Okay. Going to have something like this. And if we draw that actually it's a band. Okay, so that's the this is a cross section for using the washer method. Okay, so just this part. And what we'll do here is we want to figure out the area, okay, instead of the volume, okay, the area of the cross section, and then we're doing the integration, you know, from here to here. Okay. Now, how should we do that? Well, it turns out that you know, this is what we call the washer, and to figure out the area of this washer here, you see, we need to figure out the radius of this small circle, and also we want to figure out the maybe the radius for the outer circle, okay, capital R. And then this area gonna be pi times capital R squared minus pi times small r squared, okay? So basically it's use the larger area of the circle minus small area of the circle that are gonna give us the area of this washer, okay? Another thing is, before we try to figure out this capital R and small r, and I also want to let you know that is, you know, when we cut and formulate our cross section, the cross section, it is perpendicular to the y-axis. In other words, it depends on where, if you move in your cross section, you are moving up and down, okay? And then the limit for the integral we're going to formulate is actually from 0 to the height of this. And since this, the x-coordinate for this point is 4, so correspondingly the y-coordinate here, this is x equals 4, okay guys? I should put 4 here. And then the height, which is exactly square root of 4, which gives us is 2. So in other words, this part is 2, okay? As far as 2. So, you know, before we do anything, we know that our integral is going to be something like this, from 0 to 2 something dy. Okay. And the inside is exactly this pieces. So the next thing is we need to figure out the little r in terms of y, and also the capital R in terms of y. Okay. And it turns out that the capital R is very easy to figure out, because the capital R, which is exactly the distance from here to here, and you can see that the capital R is always 4. Okay, so that's a constant. And then the little r, which is between the distance here and here, apparently you can see that that's exactly the x, right? X is here. But we know that at this point, it lies on the curve y equals square root of x. So we actually need to solve x in terms of y. So since y equals square root of x, and correspondingly x equals y squared, so that is exactly the small radius, which gives us is y squared. So with all this, and then we can figure out the area of the cross section, which is pi times 4 squared minus pi times y squared then square. Okay. And you know, so it's pi, so it's 16 minus y to the power of 4. Okay. And then we can fill this back into here, which is pi 16 minus y to the power of 4. And you can okay. So believe it or not, and guys, the final answer is also 128 pi over 5, because we are using this, we're solving the same problem, but two different methods, but the answer should be exactly the same. Okay, so before we close this part, let me do a little bit address. So you can see that if we're going to use a washer method, okay, so and then the integral, what we formulated, which is along the x, okay, and the revolving axis, which is the y-axis, and you know that you can think about this. If you're going to use the shell method, okay, the integral will be respect to the axis that is perpendicular to the revolving axis, okay, because of the revolving axis is y, so the integral will be respected to the perpendicular axis, which is x-axis, okay, so that's why we have dx here. On the contrary, if we use the washer method, okay, and the integral will be respect to the x, the integral will be respect to the axis that is parallel to the revolving axis. As you can see that the revolving axis is y, so our integral will also be along with y. Okay, so that's a basic comparison between the shell method and the washer method. Okay, so I'll stop here, and I hope you can enjoy this video.